Actually, when you integrate, when you integrate in Trailhead, you don't know this because you don't get grades. You get this long list of everybody in the class, and there's like a little spot where you type in their grade. So I could literally give you all A's and then correct it. So I could come through with that. They won't be your final grade for the class.
Wait, but isn't that just like a time of paperwork to like correct it?
No, I just like.
Can you correct the
It would be
grade
worth
after people graduate?
That's hard to do. That's hard to do. Okay.
Just give us all A's.
All right. So after our little adventure last time, I included, I hope, spring break notwithstanding, that you have something of a recollection for utilizing the Feynman rules to calculate amplitudes for the ABC theory, because today is when it's going to get real. Today is when we're actually going to start applying the Feynman rules to an actual particle physics theory, and that is, our first example is going to be quantum electrodynamics, okay? And as you might expect, it's going to be much, much more complicated than what we saw for the ABC theory for reasons which will become apparent, but for reasons which you could probably already go ahead and guess. Now, before I actually dig into quantum electrodynamics, I want to give you a little bit of insight as to where some of those expressions we were writing down earlier came from. Come on, guys, pay attention. I know you're really excited about getting your exams back, but you should be very excited about learning this. Otherwise, I'm going to start returning your work at the end of class. So before we dig into quantum electrodynamics, what I want to do is kind of give you an idea of where the Feynman rules were coming from for the ABC theory. And so this is the part of this lecture affectionately called Mr. Feynman and Mr. Lagrangian. Okay, so what do Mr. Feynman and Mr. Lagrangian have to do with each other? So let's recall that for the ABC theory, and what I'm doing now is going to be useful when we transition to the electromagnetic interactions, because we'll be able to follow very similar steps, even though the results, Ariel, punk ass in the back of the room, eyes forward, don't make me say it again or I'm going to roll you up to the front. What I'm going to do, the process that I'm about to lay out for the ABC theory can be applied to electromagnetism, and then even though the results are going to be more complicated and less intuitive, they're still going to hold. So remember the Lagrangian that we wrote for the ABC theory was based on scalar fields, and we had three of them. We called them A, B, and C. So we had three Klein-Gordon kinetic terms. And then we allowed each of them to have a mass, and the mass terms all look the same. And I don't know why I'm writing all this. This is really a poor use of time, but now, see, I've written too much and I can't stop. It feels so good. Oh, let's just write it all. Let's add in a D. That would be awesome. No, I'm not going to do that. Minus G, and then this was our interaction term. It was a product of all three fields. Okay, and we used that Lagrangian, or we said we were going to start with this Lagrangian. It's only long because it's a repetition of everything for A, everything for B, and everything for C. But what we actually did to calculate amplitudes to then insert into the golden rule was we said, okay, everything is evaluated from lines of A, B, and C propagating particles. And the fundamental vertex was just this thing that I drew like this. And it had an A, a B, and a C coming out. But of course, we could rotate it, flip it over. We could do anything we wanted with it as long as there was always an A. Come on, kids. How many times am I going to say this? You're driving me nuts. Put your exams away and pay attention to the lecture. This is like worse than Physics 1. The fundamental vertex had to have an A, a B, and a C coming out. Okay, but we could rotate it and it really didn't matter. And then whenever we encountered a fundamental vertex, we would write a factor of minus IG. And we refer to that as the vertex factor. So if our diagram had two vertices, we would write down a factor of this squared. And then for all of the internal lines in our diagrams, we would write down these propagator factors, which took the following form. And these were virtual particle propagators. Okay, does all of this ring a even slight pre-spring break bell? Spencer?
What was that thing that you said that you did with the Lagrangian? You shoved it into something and got something out? Because before you started writing down the lines, you're like, Lagrangian, we did something with it, it sounded really important, and then lines.
And then you spaced out.
I'm still writing.
At what point in this, are you talking about today, right now?
Yeah, right now.
No, I didn't say anything about this. I said what I'm going to do. No. Listen, last time we met, I just handed you a set of rules and I made you calculate. And the rules included things like this and things like this. What I'm going to do now is I'm going to at least allude to how these rules come from the Lagrangian. And I'm going to show it to you in this context where it was pretty simple. And then we're going to follow the same prescription for the case of QED, where it will be more complicated, but the same process will apply. That's what we're going to do. Okay? There's lots of other things we can do with Lagrangians, but that's what we're going to do with them today. So, there's the systematic things that we have to extract are, first of all, what are the particle lines that we should be including in our theory? What are the vertices we should be including? When we have vertices, what are the vertex factors that we should be writing down? And then if we have internal particles, what are the propagators that we should be writing down for those particles? And the rule kind of goes like the following. So I'll talk in a minute about where to get the vertex factor. But generally speaking, the vertex factor you can literally get by looking at the interaction. Because if we look at this interaction, this is a phi A, a phi B, a phi C. It's three of them. So there's an interaction with three lines, and one of them's A, one of them's B, one of them's C. Okay? So it's probably not a huge stretch for you to guess what the vertex factor for that would look like. What would it look like? Say it again? Sorry, not the vertex factor, but what would the vertex drawing look like? Yeah, it would just be two A's and a B. Okay, so identifying what vertex you draw is not really that hard. Okay, so then how do we actually pull out the factors? And right now it's going to be really, really trivial almost. And the rules are going to be like, that's a really weird rule. Why'd you do that? But you're going to understand and appreciate it when we go to quantum electrodynamics, why we have to have these rules. So for a vertex factor, this is not my language. We can do the following. We write I times the interaction term in the Lagrangian. So this would be your interaction term. So you multiply that by I, and then you translate it to momentum space. So anywhere, if you see an IH bar d mu, we don't see one in here, so it doesn't matter. We replace that with p mu. And then you erase the field variables. And then what you have left is your vertex factor. Okay? Well, let's see if it works. Okay? So I take that interaction term. Oh, you can just say, hey, lower the screen. I'm all up on that. Okay, so we multiply it by I, and then we erase the field variables. Wow. You see that? Wow. You could have probably cooked up like a gazillion ways to get to that. Okay? Now I have to say, what I'm doing at this step is I am sidestepping an enormous part of formal quantum field theory. Like to go from here to this process is quantum field theory. We don't have time for that in this class. Okay? But I'm just trying to give you an idea of why the quantum field theory result plays out the way it does. Again, because it's going to be less trivial in the case of quantum electrodynamics. And then lastly, for propagators, we write the free particle equation of motion. So this would be the Klein-Gordon equation, the Dirac equation, or the Proca equation. Okay, not Lagrangians, but equations of motion in momentum space. So again, if we see a derivative in the Klein-Gordon equation, we would replace it with this substitution in terms of momentum. So for example, I'll just do the Klein-Gordon example. So the Klein-Gordon equation for a scalar field phi okay, and bear in mind, everything that I'm saying now is using our sort of post-formalism conventions for signs and metrics, and so there's a few sign changes if you compare this to what we had done very early in the semester. Most of you probably won't remember those signs. That's okay, but if you're ever comparing notes and you're like, wait, there was a minus there. Okay, so this is the Klein-Gordon equation. It looks different than the Klein-Gordon Lagrangian because there's a minus there, but this is the equation of motion you get from varying that Lagrangian. Okay, and then when we write this in momentum space, we can get rid of the d mu's, and we can also get rid of an overall factor of h bar. Okay, because here there's an h bar, 1 over h bar squared. When I replace these derivatives with p mu's, the p mu's will come with 1 over h bars. There'll be 2 of them, and then this whole thing is equal to 0, so you can just cancel off the 1 over h bar squared. And then once you've done this, you take this guy and you multiply the inverse of this by I to get the propagator. Okay? And there you have it. So, I mean, P is just a momentum label, and we know that for internal particles, we label their momentum Q instead of P, just so that we can remind ourselves that they're internal. So you take the factor in parenthesis, you do the inverse of it. Now, in this case, that happens to be 1 over it, but in other cases, it will be something more complicated. Okay? But you do the inverse of it, multiply it by I, and that's what you should be writing for propagators. Okay? All right. So are there any questions about that before we move into the real deal? Yeah?
Do these, so if you go through the actual field theory of it, do these steps fall out nicely? Or was it more, we knew what it should be, and in the result, we found a way to get there?
No, it's not. No, it's not so much that it falls out. It's not so much that we knew the answer. And then we found a way to get there. I mean, no, it doesn't fall out nicely. There's nothing nice about the formal development of perturbative quantum field theory. But, you know, I mean, I can send you to a gazillion references if you'd really like to follow up with it. But it's really, I mean, you would easily spend an entire semester just getting from here to these rules. But we want to actually do some calculations and get some things we can compare to experiments, so there's just not time. Okay, all right, so everybody's good with that? So what I'm going to do now is I'm going to erase all this, and I'm just going to replace that Lagrangian by the QED Lagrangian. And then we're going to do the same thing. Okay? So here we go. And on the one hand, the QED Lagrangian is obviously much shorter, but unfortunately, it is in terms of considerably more sophisticated mathematical things because it deals with spinors. So here we go. I'm going to have a class for students at the school in stealth yawning. Because there's nothing worse than turning around and just hearing
Lagrangian.
Okay, so this is the considerably shorter, not Lagrangian of QED, right? And, okay, so let's just start applying what we just talked about to this Lagrangian. So first of all, where's the interaction term? Metal. Came up first. Which of these, 1, 2, 3, 4 terms is the interaction term? This one? This is a form of an interaction. This is the self-interaction of the Dirac spinor with itself, but we give that a special name. We call it the mass term. The third one. Yeah, so the third one has a spinor, and the gauge field A. Okay? So if you were going to guess, John Bryce, what my vertex would look like, what do you think I might draw? Would it have 2 things coming out, 3 things coming out, 4 things coming out, 5, 6? 3, yeah, because there's roughly 3 things. There's 3 fields. Don't be confused. This is a constant. This is some weird spin matrix thing, but it's not a field. So there's a field here, a field here, and a field here. 1 for each. So we would have 3 things coming out. But the size are obviously something quite different than the A. So in order to distinguish what the A is, we're going to draw something different for it, and we're going to make that a squiggly line. Okay? Now, when we use this Lagrangian to describe physics, we should bear in mind that we're actually describing real-world physics. And so we can actually give the particles or the fields that we're working with actual real names. So what I have in mind is this psi describes a charged fermion. Does anyone know of a charged fermion?
An electron.
An electron, okay? So we could take the psi to be an electron, and in that case, I could draw the fundamental vertex, and it would look like this. And then this is the A mu. Okay? Couple of incredibly important things just happened, which I'm so glad some people left the room to miss. First of all, we see for the first time the appearance of arrows on the lines. The arrows on the lines are going to become very important now. We didn't see them in the ABC theory, because now we know that an electron is something different than a positron. It's antiparticle, or it's antipartner. And what these arrows are going to help us identify is whether we're dealing with an electron or an anti-electron. And the way that we identify that is really just thinking about the direction the arrow points in time. So remember that time flows to the right. So with this particular picture, this is an electron and this is an electron. However, if I rotate it, which we know we can do, well, I gave up on that diagram. My squiggly lines have got to be squiggly. Okay, kind of picky. Now we notice that we have an electron here, but we have an anti-electron here. Okay? Now you might say, well, okay, am I allowed to draw this diagram? After all, this is a fermion, it's the same fermion field, and then that's a gauge field.
I'm confused. Do the arrows denote the psi bar versus the psi?
No. Psi itself is capable of describing an electron or an anti-electron. Psi bar is just something we have to do to psi so that together they make a scalar. So be really careful. Psi bar is not the anti-electron and psi the electron. That is a common misconception in this notation. It's kind of like saying, if I have a vector, a column vector and a row vector, which I create just so that I can smash them together to make a scalar, does one of them a particle? No, that's just a convenient thing you do so that when you combine them, they make a scalar. Okay? Yes, Spencer.
So this is basically like AAB, like what you, an AAB.
It's similar to AAB, but there's some differences. For example, in the ABC theory, the particles were their own antiparticles. So there was no reason to put an arrow on them. Now, you might notice in this theory that there's a particle which is its own antiparticle. What's that?
A mu.
The A mu. And by the way, what do we call that particle?
Photon.
That's the photon, okay? And so you might or might not be aware that a photon is its own antiparticle. So there's no reason to put an arrow on the A mu line, okay? Now, so we might ask, is this a possible diagram? And if we just think about it for a moment, and this is the beauty of this notation, we realize that this can't work for the following simple reason. If this is an electron, how much charge does it carry?
-1.
-1 unit of the electron charge. If this is an anti-electron,
Positive plus 1.
it carries +1. So I have -1 coming in and +1 going out. How much charge does this carry? None. So I'm somehow having, and remember, time goes this way. So as I go through time, I start out with negative charge, and then I have positive charge. I'm not conserving charge. And we know that doesn't happen in physics. I mean, electric charge is a conserved quantity. But if you pay attention to these diagrams, you see, oh wait, electric charge is conserved. I have -1 coming in and -1 coming out. I have -1 coming in and +1 coming in. -1 plus +1 is 0, and that lets me have 0 come out. Okay? So built into the flow of the particle lines is the conservation of charge. Okay? And you'll get more comfortable with this in due time, but I want to point out early on, you should never draw a vertex like this because it simply violates conservation of electric charge. Okay? All right. Well, here's the good news. That's it. That's the only vertex in all of QED.
Wicked.
Everything in QED is built from that. Now, don't get me wrong. We can do QED for electrons, but we can also do QED for, say, muons. And I would draw a vertex with a muon, but it would be the same vertex. I would just be replacing the electron with the muon. And in fact, I could put any charged particle here. I could put a quark there if I wanted. But what's important is whatever particle comes in is the same thing that goes out. Okay? So you can get most of what you care about from QED just by thinking about electrons and photons, because after all, that's what we most often encounter in electromagnetic processes. Yes, Spencer?
Is mediator always a photon, or do you have to change it too?
The the gauge field is a photon. When you call something a mediator, I understand what you mean by that language, but I can show you some, so here's a QED diagram. I mean, now we can start making QED diagrams. So for example, before we even know how to calculate them, if I said I want to consider electron scattering, where 2 electrons come in and 2 electrons go out, how would I complete that?
Definitely a photon.
Yeah. Yes, I could just make a photon like that, and that is a valid QED diagram. Okay? However, if I had an electron coming in and an anti-electron coming in, and I was going to have an electron come out and an anti-electron come out, how could I connect that?
Still
Yeah, I could still do the same thing, right? I could I hate doing this. I like my diagrams to be cleaner. Okay? So I'm still building that out of the same fundamental vertex, right? Oh, no, I'm sorry. I totally lied here. You guys have got to... This was wrong. This was so wrong.
Two charge.
Woo!
Charge conservation is wrong.
I'm like, QED is so simple. You've only got this one. And then I draw a wrong diagram. I feel so bad. Okay, so hold on. Okay, so let me be honest about electron scattering. So how would I actually complete that diagram?
Connect 2 line balls.
Connect.
Yeah, I would connect these, and then there would be a photon between them. Okay?
Wait, so the arrow does represents what kind of particle it is, right? Not which way it's traveling?
Yes. Yes. The
So then-
travel is always so there's a couple of ways to identify the travel. We know that later, when we start evaluating these, we're going to give these momenta. And those will be additional arrows. So that's going to tell you about the direction of the momentum flow. Okay? But you can also just think about this as reading it in time.
So like
From
for
left to
the-
right.
The correct diagram, like, aren't there arrows facing opposite way, like, aren't there arrows facing opposite ways so that one's an electron, one's
Here?
an anti-electron? No, up in the left.
Here?
Yeah, like aren't there arrows facing opposite on an orientation, or are they?
Here? Well, so one way to think about the arrow is that it's the direction in which the charge is flowing. So if I say this has got negative charge, it's negative charge flowing into the vertex. No, that's not even a good way to think about it. Okay, hold on. Let me. So let me see. So I guess I don't completely understand your question.
Just, I'm confused on whether the orientation of the arrow.
When you're talking about the
represents-
arrow, you mean these arrows, not
Right,
these.
those arrows, yeah, on the lines. Is that, like, that designates what kind of particle it is?
Yes.
Right? Okay, some of them it just, I thought
So
they were
so when I draw this,
Uh-huh.
okay, and this might be the confusion. When I draw this, what I mean is this is an electron going forward in time. This is a positron going forward in time. The backwards arrow is telling me it's a positron. It's not telling me the direction it's moving. Now, of course, this is where some of the older interpretations would say an antiparticle is just a real particle moving backwards in time. I don't like that interpretation. I just like to think of everything going forward in time, and then some things are matter and some things are antimatter. Is that?
And so on the diagram then on the left, if you got a positron out, you would have the arrow reversed on those, right?
But you couldn't, is what I'm saying. You
Or
could
I know
not.
you couldn't, but if say you made a diagram that could make it, that's how it would look.
Yes.
Okay, okay.
Yeah.
That's what I said. Okay, thank you.
Okay. So, all right. So this is our only vertex from which we build things, and so the first thing we can do is write down the vertex factor. So I times the interaction term in the Lagrangian. So we have minus IQ psi bar gamma mu psi a mu. Okay. And now this is the one case where it's a little wonky. Because it turns out that a mu in the conventional units used in particle physics, a mu itself carries dimensions. And so when we erase the field variables, we can't just erase a mu, we have to erase a mu with a combination of constants so that we're erasing a dimensionless quantity. So what we actually erase for the case of QED is psi bar, we erase psi, and then we actually have to erase the square root of h bar c over 4 pi times a mu. Okay? But of course, if we do that, what we're left with is minus I square root of 4 pi over h bar c, because we have to introduce the thing that we're going to erase, times the charge times gamma mu. Okay? Now, does anybody remember what the vertex factor was for the ABC theory? It was negative IG. So we can immediately see that QED is going to be more complicated because our vertex factors include gamma matrices. Yeah, I know. Matrices in spin space, vectors in space-time, baby. This stuff is constant. That's the electric charge. But that baby right there, ooh, it's going to be a headache. It'll hurt a little bit. If you're scared, you should be scared. Okay, here we go. All right. Oftentimes, we will lump all of this stuff together and just call this I times the electric coupling times gamma mu. So sometimes if we don't want to mess around with the square root 4 pi over h bar c, we'll just write things in terms of GE. Okay, so now we want propagators. So the equation of motion in this context would be, Emily,
What's up?
what would the equation of motion that we should be using to build our propagators for this Lagrangian be? The Dirac equation, exactly. So we should appeal to the Dirac equation. So for propagators, so this is our vertex factor. Okay, so for the propagator, we should write the Dirac equation. So I gamma mu d mu psi minus mc over h bar psi equals 0. Again, there could be some sign changes from the conventions we used earlier. And then you have actually already written this in momentum space for various homework problems. But getting rid of some overall constants, we get something that looks like that. And then Patrick, where are you, Patrick? Patrick, remind me, what am I supposed to do with the thing in brackets to create the propagator? So what did we do for the ABC theory to get the propagator? Yeah, we take the inverse of this thing and multiply by I. Okay? Now, in the ABC theory, that thing we were writing down was just a scalar. So the inverse was literally 1 over it. What is this? What kind of quantity is this? Levi. What is the thing in parentheses here in the brackets?
Scalar.
It is a scalar in space-time, but
Oh, but not in
Spin space.
yeah, what kind of thing is in spin space?
just like a,
Would be a vector.
Actually, it'd be a matrix, because the gammas are matrices in spin space, and of course there's an understood identity here. So this thing is actually a matrix. So we have to take the matrix inverse and multiply by I. Okay? Fortunately, that's something which you all have roughly done in a homework assignment, where you demonstrated that you can take the Dirac equation and get the Klein-Gordon equation out of it. So you can go back and look at the notes of that. But after that process, you get an expression that looks like the following. Okay? So there is the propagator. And again, if it, for an internal particle, we would be calling these p's q's. So if it's confusing, we'll just go ahead and put it in with q's. So if you have an internal virtual particle, and by particle I mean an electron or a muon, not a photon, we'll do a photon in just a second, then this is the propagator you have to write down. Again, way worse than what we dealt with in the ABC theory, because in the ABC theory it was just basically I over q squared minus m squared c squared. It was a number. Here, matrix in spin space.
Or you just like turn P to Q for notation.
Well, I turned it to Q because we're only going to use propagators for internal particles, and when we do that, we always label the internal momentum by Q. Yeah, Will.
How do you know whether to invert it like a spin matrix or a space-time matrix? Or do you just always...
Well, no, you have to identify what the quantity is, and then you have to invert it in whatever in whatever mathematical structure it exists. So if it's a matrix, you have to do the matrix inverse.
Gotcha.
Okay, if it's a matrix in space-time, you do the inverse of the matrix in space-time. So if it's a tensor in space-time, you do the inverse of the tensor in space-time. If it's a matrix in spin space, you do the inverse of the matrix.
You do both, man.
Say again?
You do both.
Or you could do both. Well, here you don't have to do both because this is a scalar in space-time.
Right, so you just put it over it. Or I mean, you just do 1 over, but then you also have the inverse matrix on top. Is that what you're saying? Or?
No. I'm saying what I'm saying is that the inverse. So this is a matrix. I'm going to call it M.
Fine.
Okay, and you could write it down. It would be a 4x4 matrix, and then you could find the inverse of that matrix, which is defined the way we define inverses. It's the matrix such that the matrix, the inverse times this gives you the identity.
Yes.
And what I'm saying is the inverse of this matrix is going to be gamma mu q mu plus mc over q squared minus m squared c squared. Where at very least recognize that this is a 4x4 matrix in spin space, this is a 4x4 matrix in spin space. Okay?
Both scalars in space-time.
Yeah, and they're both scalars in space-time. Matt?
I think that's the question, the same one I had. Don't we have to invert it in space-time too?
Oh, you do implicitly there because it's a scalar on a
Yeah, it's a scalar in space-time, so inverting it is literally just dividing by it.
Okay.
So technically the inverse in spin space is
Okay, well-
reciprocal, and then you invert it so it's reciprocal.
Yeah, but you're not, look, you're not, no, actually, no. So, you don't, Matt, these aren't separate steps. You don't invert it in space-time and then invert it in spin space.
Okay.
This is a matrix, period. And you're doing the inverse of the matrix. It's the same as if I gave you a number k and I said find the inverse.
Okay, but if we're doing QCD and you have like a vector in space-time in a...
You're not going to encounter that.
All right.
is my point. You're not going to encounter that. So we can hypothesize about how would you invert, you know, Willy Wonka tied to Barney's butt. But that's not going to come up in particle physics.
Sounds good.
Okay? When it does, I'll let you guys know. Try and hold it together back then, Matt. It's going to be okay. You guys should make an E-Days t-shirt. Willy Wonka tied to Barney's butt. Invert that. Okay, now, so here we go. We've got one propagator. All right, but that's unfortunately not the end of the story because we know that there's going to be internal photon lines. So we also have to figure out what the propagator for the photon is going to look like. All right, and this is going to require some work. So I'm cataloging results here. You've got the vertex factor, you've got what your vertex pictures are, you've got the propagator for internal matter lines, and now we have to find the propagator for the photon. And so for the photon, we can start by writing down the equation of motion, and that's the Proc equation. And what I'm going to do now, just for efficiency later on, is I'm going to go ahead and do this for a massive gauge field, because we know when we do the weak interactions, we have to deal with massive gauge fields. So we're going to go ahead and get the answer for the weak interactions, and then we can just set the mass to 0 and figure out what it would be for the photon. Okay? But if you're going to go through this once, you should just see it with the mass. So here's the massive Proc equation. All right, when we send this to momentum space, I'm going to do the usual substitution and get rid of an overall factor of h bar and I. And so this is going to reduce to this. And you can fill in that step in the privacy of your party with Willy Wonka and Barney. Okay? And so in the spirit of what we did for the ABC theory and what we just did for the matter, what we would like to do is write this as something in brackets acting on A's, where maybe that's A nu. Okay? But the issue we see is that there's an A nu here and A nu here, but this has got a different index. So this is going to require a little bit of massaging, as my British teacher from Georgia Tech used to say. So we will massage this with the following. So first I'm going to hit this whole thing with an eta lambda nu. And I'm going to just write p mu as minus p squared, because that's what it is. Okay? And then distributing that guy, I'm going to have eta lambda nu. I'm going to collect the p squared here and the mc squared term. These are the ones that are already okay, because they multiply a nu. And then the leftover term is going to be this guy with this term. So I'm going to have my plus, and then I'm going to use this to lower the nu here and make it a lambda. Okay? And then notice this is a dummy index. This is a mu summed with a mu. So I could just as well call this new.
I love index notation.
Oh, that's so awesome. That's the best. Okay, and then, so then we can actually just treat this as one big thing acting on a new. Okay? And now we have the gentle job of inverting this quantity, which is what kind of object?
Vector matrix.
It is a 0-2 tensor in space-time. It is a second-rank tensor in space-time. It's trivial in spin space, but it's got 2 lower indices in space-time. Okay? Yeah, Joe.
Just gotta ask, why did you have to turn that into a lower lambda before you were able to switch the summed index?
Why did I have to do that?
Because the equals.
Oh yeah, because in this expression right here, if I switched that to a new, then this would be new, new, new.
Gotcha.
Which wouldn't make any sense. But this index, in this form of this expression, that index is tied to that index is tied to that index. So I have to kind of get this relabeled. And that's what
Gotcha.
this eta lambda new is doing for me. Okay? All right, so let's invert this guy and multiply by I. So if I take the inverse of this, which is a tensor inverse, and again, we're not going to worry about the details of that. I'm just going to write the answer. We get minus I times p squared minus mc squared, and then we get this nice looking thing. And don't worry, I will give you the opportunity in your homework to demonstrate that this is in fact the tensor inverse. I know, you're all so excited, you're like, I want to know! And you're going to know, because you're going to do it at home. Okay? So here, good news. This is the propagator for a massive gauge field. So when we do the weak interactions, where the bosons, the W plus, minus, and Z are massive, we'll have to use this bad boy. Fortunately for quantum electrodynamics, the A mu, the photon, is massless. So if we look at this thing, we're like, oh, I just set m to 0, which is fine here, but is not so good there. All right? So what are we going to do? What are we going to do? Can we take this and just set the mass to 0?
No.
No.
Go back to the program. Take out the math.
Well, going back is important. That's actually an important observation. The thing to remember is that when you take the mass to 0 for a vector field like A mu, it's actually a discontinuous limit. Because something changes discretely when you go from an arbitrarily small mass to being exactly massless. And what is that thing?
You lose a term in the program equation?
The velocities.
Does anybody remember? So remember when we talked about the classification of spin states, the Wigner classification, and we talked about going to the rest frame and how you couldn't do that for a massless particle. And so you change the number of polarization states. If it's massive, it doesn't matter how small the mass is, if it's massive, a vector has 3 polarization states. If it's massless, it only has 2. It's automatically transversely polarized. And that is a discrete change. Going from 3 to 2 is discrete. And usually when you try and take a continuous limit, like taking m to 0, and something pathological happens, clearly this is going wonky, chances are you're missing out on something discrete happening. So what we can do is go back up a little bit. In fact, we could go to this line, and we can remember that for a massless gauge field, we have this transversality condition that the momentum and the polarization of the gauge field are orthogonal. So this term actually vanishes. The mass is 0, so the whole equation of motion just reduces to a to nu times p squared equals 0. Okay? So for a massless gauge field, we just get minus I a to mu nu over p squared. And this is the propagator for a massless gauge field. Okay? Okay, again, if I take this equation and I use transversality, so I have p nu, a nu, these are orthogonal. That's what transversality means. The momentum of the gauge field is perpendicular to the fluctuation in the gauge field. This is 0. I set the mass to 0, and this just becomes eta lambda nu minus p squared a nu equals 0. And then I just want to take the inverse of that. Okay? All right. Okay, so now we've got the bits and pieces. We've got our allowed diagram, vertices. We've got a vertex factor. It's a spin matrix. We got a propagator for matter lines. It's a spin matrix. We got a propagator for the photon. It's a tensor in space-time. Nothing is easy. That's why we hate Dirac's house. But nonetheless, this is the real world. This is QED. And so now we want to see how do we actually apply these to do calculations. So we are now in a position to write down the Feynman rules for QED. And if you have a place in your notes where you wrote down the Feynman rules for the ABC theory, now would be a good time to just quickly look back at those. I'm certainly not going to write them down again. Here we go. Well, it's better than a yawn, I suppose. All right, here we go. So first of all, as we mentioned, diagrams are built from vertices of this form, where for now we'll just stick to electrons. We won't worry about muons and so forth. Bear in mind, if I did include muons and tauons and quarks, if I draw an electron coming in, it's always an electron on the other end. You don't turn an electron into a muon through the electromagnetic interactions.
Like, so you could, on the other end of that photon?
You could do this.
Oh, okay. You could do that. Oh my.
Yes. Okay, so that is a part of the full story of QED, but this is a rare thing to need to worry about because we don't usually, at low energies especially, we don't really mess with higher mass leptons like muons and tauons and so forth. Okay, so I just erased what I needed.
Nice.
That's a pro tip. All right, and a couple of things to bear in mind. In the ABC theory, all degrees of freedom were scalars. And that had two important consequences. Because remember, phi A, phi B, phi C, they were all scalar fields. We used the Klein-Gordon Lagrangian. We used the Klein-Gordon equation. Everything was scalar. Literally, they're like numbers. Okay? That had two important unspoken consequences, which you are now very much going to appreciate because they're going to no longer be true. And that is that order did not matter. And secondly, it was trivial to make sure m was a scalar. That is, the amplitude m for a process should be a scalar, but if all you're doing is multiplying a bunch of scalars together, The result's going to be a scalar. Okay? Now we know that in QED, because we're dealing with spinors and matrices in spin space and tensors, order is going to matter. Okay? And we're going to have to be really careful to make sure that when we put things down, we write them in a fashion that creates a scalar. Right? And I'm going to give you an algorithm for that at the end of this. Okay? But literally, when we did the Feynman rules for the ABC theory, I said, write this down, write this down, write this down. I didn't tell you write this first and then write this. Really, the only thing you had to worry about with ordering in that was to make sure the integral was all the way out on the left. And the D4 Q's were all the way on the right, just so that you were integrating. But otherwise, there was no paying attention to the order. Here, order is going to be everything. Okay? So, right, so another complication which we won't talk about today, I won't talk about it right now. Okay, here we go. So some useful expressions that we're going to make use of extensively are the following. So for everything in my theory, I've got to write down a couple of expressions that will enter into the Feynman rules. So we have electrons, positrons, and photons. And much of what I'm about to talk about is entirely hung up with the idea that when you have a scalar, really the only thing you have to tell me about the scalar is the direction it's moving and how much energy it has. Right? Because from that I can give the momentum and the form momentum, and that's kind of it. It's all the information that's in the Klein-Gordon equation. This is, of course, assuming I know its mass. Okay? But now that we have spinors, we know that in addition to the particle, the fluctuation of the field, in addition to it moving with some energy and momentum, it's also got a spin degree of freedom. What direction is the spin aligned, or how do we describe the spin part? So the new complications are largely going to be addressing that we have to talk about what the spin is doing. Okay? So here we go. For each of these, I'm going to write down a wave function. I'm going to write down the relevant equation of motion in momentum space. And this is just going to be a useful tabulation of results that we'll use in writing down the Feynman rules. We'll write down the adjoint equation of motion. We're going to write down a condition expressing orthonormality and a condition expressing completeness. The utility of everything I'm writing down is going to become apparent when we really start banging through calculations to the bitter end. For now, there's not going to seem motivated. I'm just kind of going to front load you with some useful information. So for the electron, my wave function, I'm going to write a plane wave state, so there'll be some amplitude and then some e to the minus I over h bar, the form momentum dotted with the position, and I already see myself running out of room. And this part right here is basically describing the Klein-Gordon information. It's the direction it's traveling and the energy and the momentum. Okay? Then there's going to be a piece that describes the spin. And that part I'm going to call US of P, where the U is just, it's a 4-component spinor. I'm not going to call it psi because we're going to have different letters for different things. So U is just saying U is a spinor. Remember when we solved the Dirac equation and we got those 4-component spinors, they had factors of px and py and pz and e inside of them? So the spinor depends on the momentum. So that's all this is saying. This is not a constant. It also depends on the momentum. And then this S is basically going to give me my choice of like spin up and spin down. Yes,
The
Spencer?
fact that it's parentheses make it a unit vector kind of idea.
No. This is just saying, this is literally, so this depends on the momentum p. I'm just saying there's a momentum dependence of this spinor u.
That's what that means.
And then this s is just going to take like two values, plus and minus.
But the
The fact that s is in parentheses is just telling you it's not an index that you would sum over.
Okay.
It's just a label. If this is spin up, this is spin down. And again, we're going to see what we do with all these labels as we get further into calculations. Okay, so for the positron, by comparison, the wave function is going to be very similar, except recall, and we wrote this down when we solved the Dirac equation, that the exponential dependence is opposite in sign. So where there was a minus here, there's no minus there. And then we're going to separately label the spinors for positrons as V. And then for photons, the wave function is going to be and then I'm just going to take a plane wave state for the photon. And then there's going to be a photon polarization vector. Okay, and in all of these, the value of S is 1 or 2. So for the spinors, you can think of it as spin up and spin down, and for the photon, you can think of it as the two directions orthogonal to the momentum of the photon. Now for the photon, this is just a constant polarization tensor. Whereas for spinors, as we've already seen, the spinors themselves depend on momentum. Okay. All right, so filling in the rest of this, the equation of motion for the spinors that we use to describe the electron is, of course, just the Dirac equation, whereas the equation of motion that we use to describe the spinors for the positron is actually the Dirac equation with an opposite sign in front of the mass. And then for the photon, we actually use the transversality condition. So remember, the direction in which A mu is fluctuating is the direction of the polarization. And the polarization has got to be perpendicular to the momentum. So this is just that statement of that it's transverse wave or transverse fluctuation. And then we're going to take just a gauge choice that the zeroth component of this 4 vector is 0. Again, where we're going to use all this is not obvious right now. Okay, so tabulate all this, and then you'll see where this comes in handy later on. For the adjoints, for the Dirac spinor describing a particle, we'll just have U dagger gamma 0. For V bar, our adjoint is going to be V dagger gamma 0. And for epsilon mu, we just raise the mu, and then if it's complex, we take the complex conjugate. Now, why am I bothering to talk about adjoints? Like, why is this important? Like, why are we talking about adjoints? Why am I writing all this shit on the board? Why am I teaching you particle physics? And when I took quantum field theory, I know I've told you this story, but I gotta tell you again because it's a good story. I took quantum field theory from the guy who was eventually my thesis advisor, Shanta. I hope you never watch this. And, oh boy, it's hard. And I like slept through his class, it's terrible. But I was a bad student. But halfway through the second course, this is like, these are semester-long courses. Halfway through the second course, the teacher turns around and he goes, "Are there any questions?" And this one kid in the back of the room raises his hand and he goes, "What's a field?" And the question was funny, but my advisor's reaction was hilarious. He was like, "What?" And he actually started answering it, and the kid was like, "I'm just kidding. I'm totally kidding. I'm in the second semester of quantum field theory, and I'm asking what a field is." Okay, no, seriously, why do we need to talk about adjoints? What do we use adjoints for?
Generating
Invariance.
Yeah, remember, to create scalars out of spinors, we have to use adjoints. Okay, so these are spinors, and I need to know how to form their adjoints. And eventually I'll use this to create scalars, okay? All right, the adjoint equation of motion. And then these last two things are going to become incredibly important for reasons which we won't see until probably next week, but they're going to be very, very useful. So useful that I will, of course, have you prove these in your homework. But if I take an adjoint spinor and a spinor, and each of them have a label S, and they don't have to be the same, so I'll call one S and one S prime, then these are normalized to 2mc times a delta function. So if S and S prime have different values, if this is 1 and this is 2, then this gives me 0. If this is 1 and this is 1, then this gives me 2 times the mass times c. Okay? And then I similarly have an orthogonality condition for the spinors describing the antiparticles, and the difference is that the normalization is up to a minus sign. And then we also have a normalization condition on the photon polarizations. And then, so again, this is always something times something else, and then it's just telling you whether it's 0 or something else, and if it's something else, what its value is. Okay? So this is essentially, you can think of it as like a orthogonality condition, or orthonormality condition. But do you know the difference between orthogonality and orthonormality conditions?
One versus something else.
Yeah, orthonormality is also specifying the normalization. Okay. All right. So, and then completeness, and we all know what completeness is. That thing that we always use in physics, and we're always like, God, he's going to do that again. It's like the resolution of identity. It's inserting one in a really, really cool way. That's what completeness is. So completeness, a completeness expression for in terms of spinors is that if I take US, U bar, S, and I sum over both S's, that is, I take this with S equals 1, and then I add to it this with S equals 2. That's what this is. Then this gives me gamma mu, P mu, plus MC. Okay? Now let's pause for a moment, because I'm writing a bunch of stuff up here and you're just like, oh, I'm barely keeping up. Let's just look at this for a moment. This is an adjoint spinor and this is a spinor. Together, what would they create?
Scalar.
A scalar, and that's what this is. This is a number. It might be 0, but it's a number.
Fair enough.
This is a spinor and an adjoint spinor.
Same. Oh, no, it's a matrix.
Yeah, so here you can kind of think of this as a row vector and a column vector, and those combine to give you a number. Here, this is more like a column vector, and this is a row vector, and when you combine those, you get a matrix. But that's what this is. This is a matrix in spin space.
Really nice.
Okay? I know. All right. And then we have a completeness relation for the spinors describing, and you could probably guess what this is. It's the same up to a minus sign. And then we have a completeness relation for where this is actually only in terms of the spatial components of the polarization vector. You know the best part? I haven't even written down the Feynman rules yet. It's so awesome. Okay. All right. Now, let me explain to you, or just kind of give you a hint of why these kinds of things are going to end up being useful. And again, it's going to be a bit further down the road to do this. And this is a complication I mentioned earlier. When we actually do experiments involving fermions, so if we're doing electron collisions or muon collisions or whatever, any matter for that matter, because it's all fermions, when we do experiments, normally we do not fix the polarization of what we send in. We don't say, I want to send in a spin-up electron and collide it with a spin-up electron, okay? Normally what we work with is unpolarized beams. So I have electrons coming in, and they're colliding with electrons coming in, and their polarizations are random. Okay? Likewise, when we do measurements, we don't typically measure the polarization of what comes out. We just say, does anything come out? I don't give a crap whether it's spin up or spin down. Okay? Now you can devise experiments that are polarization sensitive, but generally high energy particle experiments are not. They've got enough problems to deal with. Okay? Now what these two observations mean is that when we do calculations to get results that they can compare to what they're actually doing, colliding unpolarized beams and then not caring about what comes out, to do that, we should be doing two things with our final calculation. First of all, we should be averaging over incoming polarizations. So we don't want to say it's spin up. We want to say on average, you know, we average over all possible spin states coming in. And we sum over outgoing polarizations. Because we say, I don't care what it is. I'll take it all. Give it all to me, baby. Okay? Now we're going to do these steps in detail, and in fact, that's where a tremendous amount of the work in calculating QED amplitudes is going to be. Okay? And that's where a lot of these relationships in particular are going to become very important. But that's going to be a little bit down the road. All right? But just sort of a preview of why some of this machinery has to get put out there. Okay, so what I'm going to do to finish is, and we're going to finish on time, and then we'll start on Thursday with the Feynman rules, which I haven't even written down. Is actually give you expressions for some of these things, because remember, these are 4-component spinors, but they are plane wave solutions to the Dirac equation. These are things which we've actually solved for earlier in the semester. The reason I'm giving them to you again is because their form has changed somewhat because we've adopted new conventions. In particular, the gamma matrices are a slightly different form than what we used earlier in the semester. Okay? So again, these will be a little bit different than what you've been working with in your homework earlier. But the U1 solution is going to have a normalization of E plus, or it's going to have an overall coefficient of E plus MC squared over C. And then the 4 components are going to be 1, 0, C, P, Z over. And again, a lot of this should be familiar. I mean, it's not going to be like apples and orange compared to what we worked with before. But exactly where things are showing up and some of the normalization factors are going to look a little bit different. Okay, so if for some reason you need to have an expression for U1, remember S for all of these is 1 or 2. If you need an expression for U1, you grab this bad boy. Okay? And then for U2, should you need it, same overall coefficient. And this time we're going to have 0, 1, CPX minus IPY over E plus MC squared, and then minus CPZ over E plus MC squared. And then for the spinors describing antimatter, and folks, bear in mind, everything I'm writing here for electrons and positrons, you would use the same description if this was a muon and an anti-muon, or a tauon and an anti-tauon. Okay, because the only difference is their charge and their mass. Okay, but in terms of being spinors and all the description and the complexity of spinors, it's the same. So for here we have the same coefficients. CPX minus IPY over E plus MC squared minus CPZ over E plus MC squared, and then 0, 1, and then V2. And okay. So if you want to identify Kowalski, because you asked earlier, where are the particle and antiparticle parts of the story? The particle parts are sort of sitting in the lower two parts of the 4-component spinor. It's not entirely there because you still have something you're specifying in the top. And then for the antiparticle, it's in the upper two pieces. Of course, you could take any one of these and you could form its adjoint. Okay? All right, and then just so that you're walking away with enough information for our new conventions, these were derived from the convention that the gamma zero matrix is very different than the gamma zero matrix that we used earlier. And the gamma i's are here, where the conventions for the Pauli matrices are these. Okay? All right, so we're going to leave it off there, and when we come back next time, what I'm basically going to do is what we spent most of our time doing the last time we met, which is let's consider a process, so electron, scattering. Let's take that and draw a diagram, or however many diagrams we should draw, okay, or however many we're willing to calculate is what I should say. And then what are the actual steps for calculating the M associated with that? So we're going to have a lot of steps that we've already seen. We're going to label the momenta, label the internal momenta, the external momenta. We're going to write down our vertex factors. We're going to write down our propagators. But of course, the big difference is, A, the factors that we write down are more complicated, and B, we've got to be a lot more careful about the ordering of things, okay? And then at the end of the day, we'll have some integrals, we'll have some delta functions, we'll evaluate those, and we'll get M, okay? And we can evaluate as many as we want. And if we evaluate more than one, we'll have to combine them, and there'll be rules for combining them because there's some exchange symmetries we have to be careful about with fermions. Once we have M, we're not done, because then we have to go and do this. And that's going to be a whole nother huge process. Okay? But after this step, that's where we've actually got an expression where we can dump it into the golden rule and then extract some of the results that you've probably seen before, like the amplitude for competent scattering and so forth, which we will actually get to. Okay? All right, so that's it for today. Yeah. Did all were there a stack of exams that didn't get collected?
So no matter what you pick for arbitrary U, it's going to take on that. So anything in a sum, you can switch to crazy.
Thanks, Alex.
Because at first I was like, you can't just order these tensors and make them cancel themselves out. That would make every fucking math.
You look definitely me trying to